Believe we can go ahead and let's go ahead and transition. First up, we have Steve and Paul. If you guys want to go ahead and let's see, we'll give you control to share your screen, whoever's going to share. And if you want to bring up your presentation,
Thanks,
we'll let you
Peter.
go ahead and take it away.
Thank you. Paul's going to share a screen, so.
Okay.
Thanks for everyone that's joined. Myself, who's speaking, is Stephen Moore, the project engineer at Retal. I'm currently looking after the ORV3 development. And also my colleague here is Paul. Can you introduce yourself?
Good morning. My name is Paul Clements. I'm the design engineer at Retal CSM.
Okay, so move to the next slide, please, Paul. Today, we'll be giving you an overview of all of the OpenRack updates that we have seen since the last presentation we gave at the last show. We wanted to make sure that we weren't repeating our, so we've focused in on the areas of change since that last presentation. So here is just the contents of what we're going to cover. So first, there'll just be a very basic rack overview for anyone who's not familiar with the frame. Secondly, we'll just go over the rack frame structural analysis, which was completed on the V3 frame Rev 1 versus the V2 rack that we have today in production. Next, we'll be going through the ORV3 frame updates, which were a result of the analysis that we did. Just a breakout there of what was looked at, which included the base tray and caster plate, and also material thickness increases for individual components within the frame. Then also updated rack frame analysis based off of these updates. And following on from that, I focus on the cooling manifold hydraulic loading analysis, and then updates related to that analysis on the following slides. And part of that is the manifold support beam as a focus of the design for that analysis. And then finally, we'll finally cover any additional updates and features we have added based on feedback and requests. So some of the key parts there are the leveling feet assembly, which has been improved from the previous design. And then also finally, the spring clip design based on reviews that we have done. Okay, so here's just a couple images of the rack as it is today, bit of an overview. So some of the key features that have been pointed out there. One is the frame weld assembly, which you can see, this is just an image of the front and the back of the rack. So it is the same frame. And it's just very similar to as it was before. As you can see, a large rear vertical member, of a similar middle vertical member, and then a front vertical member, which is thin either side of the cable manager, which you can see in between there. Then there's also images of the IT and power shelves as seen in the frames. It's hard to see there which ones were power shelves, but just in the middle of the rack on the right-hand image, you can see the slightly shorter shelves are your power shelves in the frame. We have also got a 48-volt buzz bar, as you can see in the CAD there. And that's the main features that are in this overview for now. There are other components such as the cooling manifolds, which you will see analysis on that aren't in this CAD, but we'll get into that further into the presentation.
Right, okay. So there's been a fair bit of analysis on the structural members of the rack. So primarily the first natural frequency has been analysed. This is an influencing factor in a lot of the dynamic testing of the rack, the shock and vibe testing. Specific tests that this would be influencing in is the horizontal impact tests on the front and the side of the rack, and rotational edge and flat drop tests. So they all are influenced by this first natural frequency of the rack. So ORV3 passes all the tests. So that is really the target value that we're trying to get to on ORV3. So first natural frequency analysis allows for the increase in payload. So we're going from 1400 kilograms up to a 1600 kilogram payload And also the geometry changes are taken into account, such as for V3, the height increases has increased. So ORV2, first natural frequency, comes out at 2.1 hertz. And this is across the width of the rack, as you would expect. This is the sort of lowest second moment area of the rack when it's loaded configuration, and it's across the width. So when ORV3, the initial build, was analysed, it gave a first natural frequency down at 1.5 hertz. So this is significantly lower than the target value of ORV2, up at 2.1 hertz. So the next couple of slides just goes through some of the updates that have gone into the rack to get this first natural frequency up towards the ORV2 level, hopefully. So the base tray, this is quite a simple modification. The thickness increase for the complete base tray has changed. So on the left, there's an image of the isometric view of the underside of the rack. And on the right, a very similar view. It's just exploded off, and then the components which have been modified have just been highlighted red. And then additional to this, there's this spreader plate. So this is really a new component, and it adds stiffness in several ways. So it builds in this width beam member, which spans the width of the rack. That adds sort of significant stiffness to the rack. And then there are downward folds in the depth. So these casters sit within a pocketed region of the caster bracket. And then thirdly, this caster bracket is fastened to the underfolds of the base tray. So no sliding of members can occur. So all the load transfer occurs, and stiffness is given into the rack base. So how does this affect the first natural frequency? But so both of these modifications reduce the amount of frame rotation in this contact area between the base tray and the vertical members. So add stiffness in that way. So the initial proposal around the caster bracket, it's a fairly complicated component. So it was reviewed with our production engineering team, and there was certain modifications to make it manufacturable. So with these modifications included, the FEA was rerun, and just to confirm that the rack stiffness hasn't been reduced by making it sort of manufacturable. And lastly, just as a sort of side note, the caster plate offers an interfacing surface for the cooling manifold. So the next set of modifications to increase stiffness is the change to the vertical members. So you can just see in this image down in the bottom right-hand corner, the vertical members are constructed of an outer member, and then welded to this to create like a box section is the inner member. So both of those members have a material thickness increase from 2 millimeter up to 2.5 millimeter. So this adds a lot of stiffness to the region of the rack where the equipment is interfacing. So all the way up this equipment interface area, stiffness has been added by this modification. So the resulting analysis with all these modifications included, again, brings the first natural frequency within the target value and comparable with V2, so up at the 2.5 hertz target level. And again, very similar to the first mode shape with V2, it's across the width of the rack. And there you can see the shape of the moan. So just moving on to some of the hydraulic, the loading from the cooling. So this was analysed to ensure that the rack can support the forces which are distributed from the cooling. So this first image is an isometric view from the rear of the rack. You can see the cooling manifolds in the rear of the rack, left and right, and a supporting beam running across the width of the rack. So this next view just is a side view of the rack with a section from the middle of the rack. And the forces on the rear manifold pushing rearwards. So there's 28 nozzles, each with a force of 120 newtons, gives an approximate force of 3,000 newtons pushing rearwards. And opposing this is the latching in the front of the rack. So this is in 12 positions, twice the amount per latching position as the nozzles, so the overall force is the same. And this is just detailed again in a top view, a plan view, section through the rack, so you can see the force being exerted on the manifold. And then this little detail view here just shows the latching on the outer member of the frame vertical member. So the force goes directly onto the frame member, just here. And then the FEA is completed, Fea analysis, just to give an idea of the loading. Oh. So you can see just there, it's sort of pushing from the middle, and you see deformation in the manifold, upper and lower sort of regions. You see the support around the mid-height beam, and you can see the deformation around the rack datum A edge, or the edge where the latching occurs. So just looking at some of the components and some of the modifications that were made as a result of the FEA. So this rear supporting beam, the stresses were seen as high, unacceptably high. So geometrical changes were made, increasing the material thickness, and a higher grade material was specified in, so the yield of the material has increased. And then rerunning the analysis shows that the stress level is within an acceptable level. The high stresses are only spread on sort of one node regions of the mesh, so that's deemed as acceptable. We then move on to the modifications around the front of the rack, or around datum point A, datum edge A, sorry. So this beam has been added into the rack just to reduce the amount of deformation in that region. So this isometric view shows that it can be fitted sort of in the mid-height of the rack. And this front view, you can just see where it fastens onto the inner member, oh sorry, the outer member region of the rack.
Be moved, Paul, yeah?
It can be moved, yes, you're right, yes. It is sort of limited in the areas that it can be positioned within the rack, because equipment needs to be fitted around this sort of area. So additional stiffening is required. And that is done in the form of these additional webs, which sit within the inner and outer member and fasten onto the 45-degree surface of the inner member and the inside face of the outer member. So there's a sort of plan view of where it fits within the rack assembly. And the stresses generated in this component were fairly significant. So we've specified in a structural grade steel. So the yield the stresses are acceptable again around the sort of yield properties of the material. So the effect that this has had on the manifold, stresses have increased as a result of the stiffening at the front of the rack. So it's just something that I guess the manifold designers should be aware of, that stresses are beginning to raise. I think these levels are up at 200 megapascals. So it has increased slightly. So the update from the Fea analysis and the modifications. So there's reduced displacement in the width of the rack, mostly from the beam. So this reduces the failure mode around equipment delatching, and it's also a reduced displacement in the depth of the rack. So again, this reduces potential failure mode of manifold decoupling. So just moving back to this analysis, if I just get it to the right point. So as you run down this A edge, these actually include the modifications. So you can see the deformation come out around datum point A. This is highly scaled up just so the mode shape can be seen, or the deformation shape. And then this is where the web would be fitted in the rack. You can see it reduced down. And then it comes out again around your mid-height beam. And then it comes out again to your lower web. So the position of the webs has been optimized around deformation. So the final position, this deformation, this deformation, this deformation, this deformation, are all fairly equal. So the deformation is spread throughout the rack.
Okay, so there's only not much time left, so I'll just quickly scan over these last bits. But just some additional features we've added. We've updated the leveling feet assembly, as you can see from these images. There's now a smaller assembly, which includes a sliding sheet metal part and a spring clip. And this is to help improve the ease of removal for data centers. So this is an improvement here, and we'll go into some more detail in the future on how this one is operated. Next slide, Paul. So that's just the benefits there. It's easier for the elevation without needing to elevate the rack. That's part of the reason why it's better. And safety also is accounted for. And then finally, there's been some small improvements to the spring clips from the last time that we developed these. There was some float noticed on review, and also the retention force of the springs wasn't necessarily good enough for holding the shelf in place when equipment was removed. So this has been optimized with a slightly thicker clip to ensure that it snaps and it holds in place during operation. Next slide, Paul. And then finally, just a call to action for everyone. We've got the links there for both the wiki of the spec, and if anyone wanted to check the spec and designs of the latest rack, and then also any project information, Rack and Power Wiki link there, and also the mailing list. Thank you. I don't think we have time for questions, unfortunately. I don't know if we wanted to ask Caleb on that.
Yeah. No, we thanks guys. That was really good. Unfortunately, we don't have, excuse me, a lot of time for questions. Just checking the chat here, and yeah, we'll have to, I think, probably move on to the next one. I do appreciate you guys doing that.
Apologies
a lot
for
of good detail there, and
running over there.
No worries at all. And
yeah, if anyone's got any questions, feel free to email the mailing list, and also myself and Paul, we can give our email addresses for any questions.
Yeah, sure.
Yep. Yeah. Good. Thank you, guys.
Thanks, guys.
Cheers. Thanks.